This video will talk about the exponential growth model. The last video talked about a linear model. This one's going to look at an exponential growth model. When an exponential growth model, we actually have a quantity is growing by a constant factor, which means multiplication. So you're multiplying by some number to get from one time period to the next time period. Let's go with an example. It'd be helpful to look at kind of what's happening. Suppose that a bacterial culture starts with 1,000 bacteria at 8 a.m. So we know how many bacteria are there at the start. At the start, we're calling 8 a.m. And the population of the bacteria grows at a rate of 5% every minute. So if you think about this, if it's every minute, in 1 minute, we're going to have 5% more. So we started with 1,000. 5% of 1,000 is 50, because 0.05 times 1,000 is going to be 50. So you have 1,000 plus the 50, or 1,050 bacteria. In 2 minutes, you're going to have that 1,050 bacteria times another 5%. And then you're going to add it to what you started with. So you're going to take that 1,050 times 0.05 and add that back into the 1,050. Notice each time you're kind of taking your value you started with and adding this number. You can actually think of factoring out that 1,050 or the 1,000 that we started with originally and see how much you're actually multiplying by each time. And this will help us make our model. So we want to make a model, and we want to know how many bacteria are there in 1 hour. We want to know how many bacteria are there at, let's say, 5 p.m. So first thing to note is that 5% is every minute. So we do need to actually think about, again, changing that means that we're going to actually, going back to what I was kind of trying to say, is if you're 1,000 plus 1,050 for the next time, you can actually factor out the 1,000 and you get 1,000 times 1.05 to the very next time period. And then you can keep doing that each time. So this gives us our model. 1,000 is what we started with. And then 1.05, we're going to then multiply by 1.05 every single time period. And that means that we're going to have a exponential function, because you're going to multiplying every single time means you're multiplying by itself a bunch of times. And that gives you an exponential process. We want to know how much bacteria is there in 1 hour. Well, remember, this wasn't every minute. There are 60 minutes in an hour. So that would be 60 minutes. It would be the 1 hour. So we put 60 in everywhere we see a T. And we find out how many bacteria are there. Notice we started with 1,000 and now we're at 18,000 in 1 hour. That's an awful lot of growth. And that's the thing about exponential growth, is it grows very, very fast. And then we can go with how many are bacteria there at 5 p.m. Well, remember, we started at 8 a.m. 8 a.m. to noon is 4 hours. And then 4 plus 5 gives us 9 hours. And 9 hours, change it into minutes, that's going to be 9 times 60 is 540 minutes. So you're going to go ahead and put the 540 in everywhere you see a T. Go ahead and multiply out and notice how many bacteria you have in just 9 hours. Exponential growth grows really, really fast. So the exponential growth model actually looks like this. P of T, again, is the population we're looking to get after a certain time period. P0 is what you start with, whatever you decide your starting time is. 1 plus R, notice that 1.05 was just 1 plus the 0.05 rate. So 1.05 to the T. Again, P of T is your population at a certain time period. P0 is what you initially started with, whatever you call that initial time. T is the number of time periods since that initial time. R is your relative growth rate. It's a rate of the population grows, but it also can be declining in one time period. So growth means R is positive. Declining means R would be negative. So as another example, let's look at homes in Arizona appreciated 8% per year for the last 5 years. In 2010, the population actually had the value of the house was 225,000. So this isn't actually population, this is value instead of population. And we know that that means that's our starting point, because we're going to decide that 2010 is our starting time. Granted, people lived in this house before then, the house had a value before that, but we're going to call this our time zero time that we're dealing with. The rate, because it's 8% per year, that also tells me it's an exponential growth model because it's a percentage and a per year. Anytime you see percentage and per year, you think exponential growth model. Your R is 0.08 because it's 8%. And so we're going to look at our growth model. I would highly suggest you write down on a piece of paper both the exponential model and the linear model, so you have one place to look at to just decide which model you want. The minute you decide it's the exponential model, write down this formula, and then you can just put in the pieces you know. In this case, we know P0, we know R. We're going to put in certain T's later, and we're going to find P of T. Sometimes you know P of T for a certain time, and you're going to find P0 or find R. So it just depends on what you're looking to find in each case as to which one you want to deal with. Sometimes you want to solve for T. Just depends on what you're looking at. So P of T is equal to, in this case, 225,000, 1 plus 0.08 to the T. And I wouldn't leave it as 1.08. I'd write it as 1.08 instead of 1 plus 0.08 to the T. So we want to know, let's say we want to know how much it's going to be appreciating for the last 5 years. So our time, we're dealing with years, so we can just put 5 straight into it, come up with this, and you can see, wow, this house actually started at 225,000. In 5 years, it's over $100,000 worth more, so $330,000 now. And that's an exponential growth model.